Colligative properties, freezing point depression, and molar mass. The objective of this experiment is to determine the molar mass of an unknown solid. This will be accomplished by observing the freezing point depression resulting from dissolving a small amount of unknown in cyclohexane. The addition of a solute to a pure solvent will introduce new solvent-solute intermolecular forces between the solvent molecules and the solute molecules. In order to form a solution, the solvent-solute interactions must be comparable or stronger than the solvent-solvent and solute-solute interactions when the two are separated. These new, strong solvent-solute interactions cause the solvent molecules to be less likely to escape into the atmosphere, thus resulting in a lowering of the vapor pressure of the pure solvent. The vapor pressure lowering is an example of a colligative property. Colligative properties do not depend on the identity of the solute, but only the amount. The vapor pressure lowering is responsible for three additional colligative properties: boiling point elevation, freezing point depression, and osmotic pressure. Since the extent of a colligative property depends on the number of moles of solute present, we can calculate the molar mass of a compound by observing the colligative properties of a solvent that dissolves the unknown. In this experiment, we will investigate the freezing point depression of cyclohexane. This figure demonstrates the effect of vapor pressure lowering on the freezing and melting points of a pure compound. The solid blue line is the phase diagram for the pure compound. When a small amount of solute is dissolved in the pure solvent, we see that the vapor pressure curve on the right is lowered. At the same time, the melting curve on the left is also lowered in order to maintain the triple point. Consequently, the normal boiling point of the solution is pushed to a higher temperature than the pure solvent, and the normal freezing point is pushed to a lower temperature than the pure solvent. These are the resulting boiling point elevation and freezing point depression. Being a colligative property, the freezing point depression depends only on the amount of solute present, not its identity. Because of this, we will need a measure of the concentration of the solute in the solution. The freezing point depression depends on the molal concentration of the solute. The molal concentration, denoted lowercase m, is defined as the number of moles of solute divided by the number of kilograms of solvent. Let's consider an example of molal concentration calculations. We can calculate the molal concentration of 150.2 grams of sucrose, which has a molecular weight of 342.30 grams per mole, in 500 grams of water. To begin, we need the moles of sucrose. This is calculated as the mass of sucrose divided by the molar mass, which is equal to 150.2 grams times 1 mole over 342.3 grams, which gives 0.4388 moles of sucrose. The 500 grams of water is equivalent to 0.5000 kilograms, and so we can now compute the molal concentration. This is equal to the moles of sucrose divided by the kilograms of water, or 0.4388 moles of sucrose divided by 0.5000 kilograms of water, which gives a molal concentration of 0.8776 molal. The freezing point depression, denoted delta T sub F, is defined to be the difference between the freezing point of the solution and the freezing point of the pure solvent, or mathematically, delta T sub F is equal to T sub F for the solution minus T sub F for the solvent. In turn, the freezing point depression is directly proportional to the molal concentration of the solute. We can write this as delta Tf is equal to negative I times Kf times m. Here, lowercase m is the molal concentration, and Kf is known as the molal freezing point depression constant, or the cryoscopic constant, which has units of degrees Celsius per molal. The values of Kf are tabulated. The variable I is known as the Van't Hoff factor, and it accounts for the number of ions generated by an electrolyte. In this experiment, I will always equal 1. Let's consider an example of how to use the freezing point depression equation. We will determine the freezing point of the sucrose solution from the previous example. For water, the value of Kf is equal to 1.86 degrees Celsius per molal, and the molality of the solution from the previous example was determined to be 0.8776 molal. The first step is we need to calculate the freezing point depression. Recall that delta Tf is equal to negative I times Kf times m, where I is equal to 1. This is equal to negative 1 times 1.86 degrees Celsius per molal times 0.8776 molal, which gives a freezing point depression of negative 1.63 degrees Celsius. Next, we recall that the freezing point of pure water is 0.00 degrees Celsius, and we can calculate the freezing point of the solution as Tf for the solution is equal to Tf for the solvent plus delta Tf, or 0.00 degrees Celsius plus a negative 1.63 degrees Celsius, which is equal to negative 1.63 degrees Celsius. The colligative properties can be used to determine the molar mass of unknown compounds. In this experiment, we will use the freezing point depression method to calculate the molar mass of an unknown solid. The general steps involve the following. First, we determine the freezing point of the pure solvent. Second, we weigh out a known mass of unknown and dissolve it in the solvent. Third, we determine the freezing point of the solution. Fourth, we calculate the freezing point depression. Fifth, we calculate the molal concentration and then the moles of the unknown solute. And lastly, we divide the mass of the unknown by the moles of unknown to determine the molar mass. We are now ready to discuss the experiment itself. In this experiment, we will use cyclohexane as the solvent. You will measure out 10.0 milliliters of the solvent. The mass of the solvent will be calculated using the density of cyclohexane, which is 0.7726 grams per milliliter. Next, you will need to construct an ice bath. This will be a mixture of ice, water, and sodium chloride in an 800 milliliter beaker. The addition of salt will cause the temperature of the ice-water slush to drop below 0 degrees Celsius, allowing for faster freezing. The freezing point apparatus consists of two nested test tubes. The cyclohexane is poured into the inside test tube. A thermometer is inserted into the cyclohexane to record the temperature. Additionally, a stirrer made out of copper wire is also added. This will allow you to stir the cyclohexane to ensure even cooling as the freezing occurs. The test tubes are then lowered into the ice bath, and the temperature is recorded every 15 seconds until it levels off during the freezing process. Once you record at least 5 readings that are basically unchanged, you can raise the test tubes out of the ice bath and let the cyclohexane reliquefy. A plot of your temperatures versus time will give a cooling curve like the upper curve shown below. The plateau indicated by the dashed line will be the freezing point of the pure solvent. You will repeat this process once more for the pure cyclohexane. At this point, you will weigh out between 0.3 and 0.4 grams of unknown and dissolve it in the cyclohexane. Once accomplishing this, you will repeat the process for the solution 2 times. The freezing point will be lower, so a plot of your temperatures versus time will give a cooling curve like the lower curve shown below. Again, the plateau, indicated by the dashed line, is now the freezing point for the solution. The freezing point depression is then calculated as the difference between the two freezing temperatures. From the freezing point depression, the molal concentration and the number of moles of unknown can then be calculated. Lastly, the molar mass can be determined using the known weighed mass of the unknown and the calculated number of moles. In a forthcoming video, detailed information regarding the calculations and data analysis will be presented.